So we are going to talk about the independence among random variables. So we have random variables x and y. Sometimes these random variables are dependent, sometimes they are independent. So if you remember the example in the beginning of this chapter, so we were talking about an automobile, a randomly selected automobile, and the odometer value of this randomly selected automobile and the second-hand price of that automobile are two unknown random variables for us. So we can see the automobile, maybe we can predict it, but we cannot be sure about the second-hand price and the odometer value of that automobile because we do not know many things. For example, we do not know the accident records of that automobile, or we do not know the odometer value actually. Okay, so we do not know anything about this. So because of that reason, we cannot make solid predictions on these values. However, we know that they are random variables which are tied to the same object, and that object is the automobile. Because of that reason, they possess dependence, as we have said. If, for example, the odometer value is less, then we expect the second-hand price to be larger. Or if the odometer value is large, okay, so if the automobile has traveled a large amount of kilometers, then we expect the second-hand price to be low, okay? So these two random variables, they possess some dependence. However, in real life, there are some random variables which are independent from each other as well. For example, we have talked about the independence of the events, right? So just like that, the random variables can be independent as well. So they may not show any dependence between each other. For example, for a student, the grade that student takes from Calculus 1 course and Calculus 2 course final exams, they are dependent, okay? If the student is interested in mathematics, if the student studies well enough to mathematics, and if the student feels okay in mathematics exams, in that case, most probably, both grades are going to be large. Or in other words, we can say that for a student who gets a large grade in the Calculus 1 final exam, the student is expected to take a large grade in the Calculus 2 exam as well, okay? However, usually, the courses such as calculus and history are independent from each other. Okay, not in every case. I mean, a good student is usually a good student in all of the courses. However, we cannot show that the dependence between the Calculus 1 and Calculus 2 grades are as, the dependence between the calculus and history grades are as strong as the dependence between Calculus 1 and Calculus 2. So we say that, for example, if a student takes a good grade in calculus class, we cannot make any predictions on the grade that the student takes in the history class. The student can still get a good grade or a bad grade in the history class because these courses are totally different from each other. Even though the two random variables are tied to the same object, to the same student, we cannot say that they are dependent to each other, okay? So actually, because of that reason, we need to understand if two random variables are dependent or independent. Now, if two random variables are dependent, this is actually a good thing. If they are dependent to each other, this is actually a good thing because the knowledge on one of the random variables here can increase the prediction accuracy on the other one, okay? If two random variables are dependent on each other, for example, Calculus 1 and Calculus 2 grades of the same student, if the student tells me his or her Calculus 1 grade, I can make a better prediction for Calculus 2 grade, okay? But my prediction for the student's history grade is not going to be as good as the previous one. So dependence is a good thing, but at this point, we need to understand independence, okay? So when two random variables are independent from each other. So we have two random variables, x and y. X and y are said to be independent if and only if for any two real numbers, a and b, the probability of x being less than or equal to A intersection y being less than or equal to B is equal to the product of the individual probabilities of x being less than or equal to A and the probability of y being less than or equal to B. So the joint probability of x and y to be less than or equal to respectively A and B, if that joint probability, if that intersection probability is always equal to the probability of x being less than or equal to A times probability of y being less than or equal to B for any two real numbers A and B, if this equation always holds, then we say that these two random variables are independent from each other. Okay, x and y are independent from each other. So in other words, if I replace this joint probability statement with the joint cumulative distribution function of x and y at A and B, and if I replace these marginal cumulative distribution functions as marginal CDF of x at A and the marginal CDF of y at B, now I say that two random variables are independent if this equation holds for all couples of A and B values, for any A and B that you define. If this equation holds for all possible couples of A and B, if this equation holds, then they are independent. Or if they are independent, then this equation is supposed to hold for all possible values of A and B. Okay? So this is the definition of independence. The general definition of independence for any two random variables. Now, basically, it says that instead of calculating the intersection of two events based on random variables, calculating the probability of that, if we can calculate the individual event probabilities and multiply them, if that probability is going to be the same as this one, in that case, these two random variables are independent. Now, remember, we could have defined the independence statement like this, right? So if you remember chapters ago, we have defined the independence statement between two events. We say that two events are independent if and only if the intersection probability is equal to the product of the individual probabilities. So this means, so that is a very, very large dot. Okay, so let's make it a little small. If the product of the individual probabilities of two events is equal to the probability of the intersection event, then we say that A and B are independent. Okay, they are independent. So, or they are independent, then this equation always holds. So this is a similar situation here. We say that if for all possible values of A and B, the joint CDF of x and y at A and B is equal to the product of the marginal CDFs at A and B, then these two random variables are independent. Now, of course, we are not going to define the independence statement just by looking at the CDF, because as we have previously said in the beginning of this chapter, in most of the cases, we practice the joint distributions with joint probability mass functions or joint probability density functions. So let us practice the independence over the probability mass functions for two discrete random variables. So let us define the independence statement again for two discrete random variables, x and y, and the condition of independence for these two random variables to be independent. Then we say that for all possible values of lowercase x and lowercase y, the joint PDF at x and y should be equal to the product of the marginal PDFs of x at x and the marginal PDF of y at y. If this equation is true for all possible values of x and y, for all possible joint probabilities, if this equation is true, then we say that these two random variables are independent. However, if for any real couple of x and y, if this equation is not true, if this is not equal to if the joint probability mass value is not equal to the product of the marginal probability mass values, if for any of them, okay, it doesn't matter how many, if at least one of the joint probabilities, this equation does not hold, then we say that they are not independent. These two random variables are not independent. My friends, usually we use the term not independent. So we do not say X is dependent on Y or Y is dependent on X. We usually use the term X and Y are not independent. Okay? So they are either independent or not independent. So there is not a terminology such as they are dependent. Okay? Now we are going to see if these two random variables, X and Y, are independent or not. So we have a joint probability mass function here that belongs to X and Y random variables here. As you can see, there are 4 different cases. Both X and Y can be equal to 0. X can be equal to 0 and Y can be equal to 1. X can be equal to 1 and Y can be equal to 0. And both of them can be equal to 1. In that sense, one can easily understand that because both X and Y can only take 0 and 1 values, X and Y random variables here are Bernoulli random variables. Okay? But they are given, their joint probability mass function is given in this question. And we have the joint probability mass values as 0.18 for 0, 0, 0.12 for 0, 1, and we have 4K and 3K for 1, 0, and 1, 1. So before answering this question, if X and Y are independent, we need to determine the K value here, the constant K value here, right? So how are we going to determine the K value here?